you go. Okay, so yesterday we lectured on section 3.5. It was just a brief presentation on that section. But let's go over some of the problems that I assigned. Again, there's no problems on the syllabus for sections 3.3 and 3.5. We're doing a little bit more than what the syllabus, has for the course. It's important stuff, and I think it deserves a little more attention than what was required on the syllabus. So, let's go back to section 3.5. I can find it. 3, 3.4, 3.5. No, that's 3.6. All right. So 19 to 35, the odd problems. So in all the questions, it says to factor the polynomial completely and find all of its zeros, calls them zeros or roots. So section 3.5, so let's do number 23. So f of x, or what do they call it? P of x is x to the third plus 4x. So when they say factor completely, they mean into linear factors and irreducible quadratic factors. So this quadratic factor, x squared plus 4, that does not factor any further over the real numbers. That one has the complex roots that we were talking about yesterday. But once you get to here, right, now that it's factored and you set it equal to 0, this means x is equal to 0. Excuse me. Or x squared plus 4 is equal to 0. The x squared plus 4 equal to 0 means x squared equals negative 4, which means absolute value of x is the square root of negative 4. And as a and as a point of notation, we call that, right, the square root of negative 4. I'll take an extra step. Plus or minus the square root of 4 times the square root of negative 1. Square root of negative 1 is this thing we called I. So you have 2i and minus 2i. Right, so we've got 3 roots. Right? 3 roots or zeros. 0 itself, 2i and minus 2i. So that's 23. 25. So x to the fourth minus 1, calling it q of x. So factor completely. Well, you can start by noticing that this is a difference of 2 perfect squares, right? So it's the difference of x squared squared and 1 squared. So this factors as x squared minus 1, x squared plus 1. Of course, x squared minus 1 will factor further to x minus 1 and x plus 1 equals 0. So now this is factored fully into linear factors and irreducible quadratic factors. right? And we set that equal to 0. So this means x minus 1 is equal to 0, or x plus 1 equals 0, or x squared plus 1 equals 0. This one means x is equal to 1. This one means x is equal to negative 1. And this one means x squared is equal to negative 1. So x is equal to the square root of, plus or minus the square root of negative 1, which is I or minus I. All right, so we've got 4 roots. All right, 1, negative 1, I, and minus I. Again, as I was mentioning yesterday, we see the niceness of this notion of complex numbers in that a polynomial of degree n gets to have n roots all the time. That's the fundamental theorem of algebra. So this is a polynomial of degree 3. We got 3 roots. And then, of course, you can always have different multiplicities, like a root can have multiplicity 2. But adding up the multiplicities of the roots will give you the degree of the polynomial. Polynomial of degree 4, we got 4 roots. 1, negative 1, I, and negative I. And actually, this polynomial is very interesting. It's a specific example of the polynomial x to the n minus 1. So for any n, for n just bigger than or equal to 2 in this instance, right? I mean, how many roots are there in the real numbers, right? So x equal to 1 and negative 1 are the only real roots. Right? But when you look in the complex or imaginary numbers, within the imaginary numbers, so within the complex number plane, so within the complex number plane, so it's this two-dimensional plane where this is the real axis, it's called, and this is the imaginary axis. And then you put this number a plus bi, like right there. So like this is a on the real axis, b on the imaginary axis, and you plot a plus bi right here. And then the roots of x to the n minus 1 are evenly spaced points around this circle. So like for n equal to 6, so those red points are the roots of x to the 6 minus 1, and there's 6 of them. This one is 1, this one is negative 1, and these are other points that we can't really describe without talking about trigonometry a little bit, but just another just sort of note about the complex numbers and why they're a worthwhile idea. Just that it tells a good story. That's just one reason. All right. So that was 25. 27. Let's see. 29. So we've got p of x is x to the third plus x squared plus 9x plus 9. And you can factor this by doing that grouping business. Sorry, x squared, x plus 1 plus 9, x plus 1. So this becomes x plus 1 times x squared plus 9, right? So to find the roots or the zeros of this thing, right, you have x plus 1 is 0, or x squared plus 9 is 0. This one means x is minus 1. This one means x squared is minus 9. So x is 3i, or negative 3i. All right, so polynomial of degree 3, 3 roots in the complex numbers. Now, of course, as I was mentioning also, I mean, in lots of examples, contexts in which you do um, run into polynomial equations, you're not interested in the complex roots. You're only interested in the real ones. But they are there, and they do have their uses. But like oftentimes, if you're looking, I mean, sometimes like with equations, you're only interested in not just real solutions, but positive real solutions. Like if the solution is supposed to be the length of something, right? The length of something is a positive real number. It's not a negative number, nor is it a complex number, nor is it even 0. Um, 33. So p of x is x to the fourth plus 3x squared minus 4. So factor completely and find the roots or the zeros. So again, you can think of this as x squared squared minus 3x squared plus 4. So this is one of these polynomials where you think of the variable as x squared, right? So then it becomes a quadratic polynomial in x squared. So this factors as, I think I didn't write that down wrong, plus this minus 4. So this is x squared, what do we got here, plus 4x squared minus 1, yeah? Yeah. So this factors some more, x squared plus 4, that doesn't factor. This one, x squared minus 1, is x minus 1, x plus 1. So to find the roots, you set x minus 1 is 0, or x plus 1 is 0, or x squared plus 4 is 0. This one tells you x is 1, x is minus 1. This one, x squared, is minus 4. So x is 2i and minus 2i. And we don't seem to be getting roots other than that sort. So what did I ask you to turn in? 24 and 32. Yeah, 24 and 32. So let's do something like those. So this one is like what we just did. This is like number 32. For 24, we can do like 24. Well, 23 is kind of like it, but not really. So here is something like 24. So p of x is equal to x to the third minus 8x squared plus 17x. All right, factor and find the roots. So factor out an x, common factor. So x squared minus 8x plus 17. Now, this one does not factor. This one, 17 only factors as 17 and 1. And it's positive, and, the only possibility is positive 17. This is a negative 8, so the only possibility to factor over the integers would look like that. But, of course, that's wrong, because you would have to have 18x minus 18x here, which you don't have. So that doesn't factor any further. So here we're fully factored. Right, so now this means x is equal to 0, or x squared minus 8x plus 17 equals 0. And now, with the irreducible quadratic, you can find the roots in two different ways. You can complete the square, or you can use the quadratic formula. So find the roots by completing the square. Or quadratic formula. All right, I'll complete the square, and then we'll do it with the quadratic formula, and you see that we get the same thing. So this is x squared minus 8x equals negative 17. So you're going to add 16 each side. All right, this is x minus 4 squared. Oh, I'm sorry. No, 16. That's right. So this is x minus 4 squared, and this is minus 1. Right, so absolute value x minus 4 is the square root of negative 1, which is I. Right, so x minus 4 is plus or minus I. Right, so x is equal to 4 plus or minus I, right? So the roots are 0, 4 plus I, and 4 minus I. So 3 roots for the degree 3 polynomial. And now the roots are a little bit different. They're not just simply, multiples of I. They're, actual multiples of I plus a purely real number. Right, so, that's one way to find the roots. And, normally when we would get to this point, we would say there's no real roots. But, I mean, if we're just interested in what the roots are and we don't care if they're real or not, then we can take the square root of negative 1 and we're fine with it. Of course, you can also use the quadratic formula. Which is that x is equal to minus b plus or minus the square root of b squared minus 4ac over 2a. So in this case, what do we have? Minus b is 8. B squared is 64. Minus 4 times 17. Over 2a, which is just 2 in this case. 4 times 17 is 40 plus 28 is 68. So this is, 64 minus 68 is minus 4 over 2. So x is equal to 8 plus or minus 2i over 2. So that is equal to 4 plus or minus I. All right, so that's 4 plus I, or 4 minus I. All right, so you get, of course, the same thing by using the quadratic formula as you do by completing the square. So you can use whichever method you're most comfortable with. Okay, I think that is a decent selection of problems there. Yeah. All right. So let's move on to the next section, section 3.6. Kind of a lot to say in this one. So section 3.6 is on graphs of rational functions. So remember, a rational function is of the form p of x over q of x, where p and q are polynomials. Okay, so we're going to concentrate on graphing those where the degree of p is less than or equal to the degree of q. So we will show how to graph y equals px over qx. We'll not show how to graph. We will discuss the graph. When the degree of p of x is less than or equal to the degree of q of x. We could actually do more, like in general, like if the degree of p is whatever. But the most important case is where the degree of p is less than or equal to the degree of q. And as you recall, we know how to actually do division of polynomials from the previous section, so that, like, you divide p by q, and then you get a remainder whose degree is less than the degree of q. So in that sense, like, this is the most important case. So we're going to do less than or equal to, but less than is more or less, when they're equal, it's very similar to strictly less than. I'm sorry, guys. I have to get up for just a second. I'll be right back. Apologize for that. All right. So first of all, let's consider p and q to have the same degree. And let's talk about the end behavior. Okay, end behavior. Suppose that the degree of p of x, the numerator, is equal to the degree of q of x, the denominator. Okay, for simplicity, we'll just assume degree 3. Well, degree 4. Okay, so let's look at the function, this rational function. Well, let's call it r of x since it's a rational function. Rational function r of x equal to, so degree 4 divided by degree 4. So a 4 x to the fourth plus b 4 x to the, or b a3 x to the third plus a2 x squared plus a1 x plus a0 over, same thing, just with b's. So this is a polynomial of degree 4. You guys are okay with subscripts, right? What do subscripts mean? When I say a subscript 1, a subscript 2, subscript 3, subscript 4, what does that mean?
Just different ways to tell them apart.
Yeah, they're just different variables or different unknowns. I mean, as opposed to, I mean, you know, if you're gonna use different letters, like, you know, ax to the fourth plus bx squared plus c x to bx to the third cx squared plus dx plus e f x to the fourth plus g, right? You'd have a b c d e f g. I mean, you don't have to go through the whole alphabet, so you just use subscripts. They just mean different variables, but they're all called a0, a1, a2, a3, a4. Okay, what happens when x is big? Of r of x when x is huge. So x equal to a billion, something like that. Like, you know, what's the deal? Okay, well, consider the following. Take r, and what I'm going to do is multiply it by 1. Multiplied by 1. Okay, but I'm going to write 1 like this. 1 over x to the fourth over 1 over x to the fourth, like that. Right, so looking like such. So now I'm going to distribute this through here. So this becomes what? a4 x to the fourth divided by x to the fourth. So it just becomes a4 plus a3 x to the third divided by x to the fourth. So that becomes a3 over x plus a2 over x squared plus a1 over x to the third plus a0 over x to the fourth divided by, same thing on the bottom, but with b's. Oops, I forgot my plus, didn't I? The older I get, the harder it is to write in a straight line. Alright, so these become b's now on the bottom. Oh, that's right, I forgot my plus here. So B4, B3, B2, B1, B0. Alright, so now if x is huge, so if x is a billion, so the coefficients are just sort of ordinary numbers. You know, just sort of everyday numbers. Like in the examples we're talking about, like, you know, 5x to the fourth plus 8x squared plus 3x minus 12, something like that. And now we're looking at, you know, I mean, whatever it is, you only have just a few four numbers there, 5 numbers. So x is huge, a lot bigger than any of those numbers. So x is a billion or 10 billion or, a quadrillion or a gazillion or however large it needs to be. It's just much bigger than all the coefficients. Fine. What's this? If x is gigantic, what's a3 over x? Approximately. When x is huge, so x is 10 billion, what's a3 over x? So a3 is like 5. So 5 over 10 billion. What is it, approximately?
Really small.
Yeah, so it's approximately what? I mean, it's such a small number that you would not care about it, as if it were any different than the number what?
Zero?
Zero, exactly. Yes. It's effectively zero. Right? So when x is really, really large, this number is effectively, but not actually, the following. Equal to a4 plus 0, 0, 0, 0. All of these are about 0. b4 plus 0, 0, 0, 0. So just a4 over b4. It's not exactly that. It's approximately this. And the larger x gets, the closer it gets to that. a4 over b4. So, for example, for x really huge, 3x squared minus 8x plus 12 over 2x squared plus 9x plus 15 is approximately 3 halves. Just take the ratio of the leading coefficients. Right? Here it's a4 over b4. Here it's just 3 halves. Approximately. It's not exactly 3 halves, but effectively 3 halves. Right? I mean, I'm not even going to, plug it into the, we see that that's the case. All of these terms are effectively 0. All of these terms are effectively 0. Not actually, but it's the difference between that and 0 is so minuscule you really don't care. And these numbers are just constants. So that's what it equals. Now, when the degree of the numerator is less than the degree of the denominator, then the fraction is 0. So by a similar argument, if the degree of the numerator p of x is strictly less than the degree of the denominator q of x, then when x is huge, p of x over q of x is approximately 0. For example, if I took this same fraction and just increased the degree of the numerator, say, or the denominator, say, whoops, paste. So for x really large, because the degree of the numerator exceeds that of the denominator, or the degree of the denominator exceeds that of the numerator, this is approximately 0. Okay, so if the degrees are the same, it's the ratio of the leading coefficients. So in this case, 3/2. If the degree on the bottom is greater than the degree on the top, then for x huge, it's approximately 0. Effectively, because the leading coefficient of x to the third here would be 0. So you'd get 0 over 1, which is 0 in that case. All right. So that's the end behavior of the graph of a rational function. It has this thing called a horizontal asymptote, which is the ratio of the leading coefficients, or it's 0. Okay. Other things that happen. You also have vertical asymptotes. So suppose, so this means that, the graph of a rational function, of this rational function here, I mean, it does stuff over here, don't know what, but towards the end, it's going towards 0. So it's hugging the x-axis in some way, either above or below. Here, the graph of this function, I mean, it's doing whatever for small numbers here, but then after a while, this is the line y equals 3/2. The function is just hugging the graph, hugging the horizontal line, y equals 3/2, like that. So these are called horizontal asymptotes. And then you also have, for rational functions, vertical asymptotes. Okay, suppose that p of x, p of a is not 0, but q of a is 0. Then, for x very, very, very close to a, p of x over q of x, right, is close to, well, the numerator is p of a, so it's close to p of a, and down here, it's close to q of a, which is 0, so very close to 0. So it's p of a, which is non-zero, over something very close to 0. Well, what kind of number is that? So I take a non-zero number, 3, and I divide it by something really tiny. So 3 divided by 0.000000000000001. 3 divided by 0. So something close to 0, but now you can't divide by 0, yeah? You can't divide by 0, but I can divide by anything that's not 0, including something that's really, really tiny. And then you get what? What's this number here? Not what is it actually. What is it?
Huge number?
It's huge. It's an absolutely huge number. And the smaller the denominator gets, the huger the fraction gets. A really, really huge number. So when you're looking at the graph of y equals p of x over q of x, close to x equal to a, so here's the horizontal or vertical line, x equal to a, the graph of the function y equals px over qx, it climbs up this line. It shoots out towards infinity, either positive infinity or negative infinity, depending on whether it's positive or negative. And we'll talk about that in a moment. Right? So when the numerator is non-zero at a and the denominator is 0 at a, then you have this vertical asymptote. If both the numerator and denominator are 0, then you just have a hole in the graph. Or, well, you could have an asymptote too. Kind of don't really want to talk about that situation. We'll see. Maybe we'll get to that. All right. So we know about the end behavior of the graph. We know about these horizontal asymptotes. All right, so end behavior, I guess I should call it end behavior and horizontal asymptotes. It's a silly word. End behavior, horizontal asymptotes. So, you either have a horizontal asymptote at some non-zero number, or you have a horizontal asymptote at 0, which is the x-axis itself. And then you have these vertical asymptotes when the rational function has division by 0, but the top is not 0. When the top and bottom are both 0, then you have to do there's other considerations, but let's leave it at this for now. And then, well, there's other things, other considerations. There's also like, when is the thing positive or negative? Well, we know how to deal with that, right? You just look at the intervals on the real number line, and you test these intervals for positive and negative behavior. And now once you've got that, well, you can get a reasonable approximation of what a graph of such a function is going to look like, coupled with the assumption that the graph of a rational function the same assumptions we had before. They are smooth and unbroken. And, well, we just need this one. Sorry, the other one was about end behavior, but we also talked about that. So now we can get an approximation of what the graph of a rational function looks like and we can assume such graphs are smooth and unbroken, except for the vertical asymptotes. So how about this? X over x squared minus x minus 12. Well, let's factor the bottom. right? So the top of this fraction is equal to 0 at x equal to 0. The bottom of this fraction is equal to 0 at 4 and 3. Aside from that, 4 and negative 3. Aside from those points, right, neither the top nor the bottom is 0. Okay, and because the graph is going to be smooth and unbroken, okay, the only place you can switch from being positive to negative, right, are at this point, and this point. So the function is entirely positive or negative here, entirely positive or negative here, entirely positive, negative here, and here as well. So all you have to do is the same procedure that we've been doing, is just test one point in each interval to see whether that function is positive or negative. So let's look in here. We'll take x equal to negative 5. This on the top is negative, and on the bottom they're both negative. So the whole thing here is negative. Here, say x equal to minus 2. So at x equal to minus 2, this is negative, positive on the bottom, negative on the top. So the whole thing is positive. And then at x equal to positive 1, this is positive, negative, positive. So the whole thing is negative. And from 4 onward, we'll say x equal to 5. All of those three factors are positive, so the whole graph, the whole function is positive. So the function, the rational function, is 0 at 0. And f of x has vertical asymptotes at x equal to 4 and minus 3, because at 4 and minus 3, the bottom of the fraction is 0, but the top is not. Now, of course, 4 and negative 3 are not part of the domain, right? So they're actually not part of the graph. It's just a feature of the graph that happens at these points. The graph actually doesn't use these in its domain, 4 and negative 3. Okay, so let's, I'm sorry, and the degree of the top is less than the degree of the bottom. So we have a horizontal asymptote at the x-axis. So vertical asymptotes at 3 and negative 4, horizontal asymptote on the x-axis itself, and then we cross the x-axis at x equal to 0. So 1, 2, 3, we'll say right here. 1, 2, 3, 4, we'll say right here. All right, and aside from that, let's see, we are negative right here. We are negative in this interval. We are positive in this interval, negative in this interval, and positive in that interval. All right, because this is at x equal to minus 3. And this is x equal to positive 4. And then we have a horizontal asymptote there, so it's got to look like this. See? Horizontal asymptote, vertical asymptote, and negative, and smooth and unbroken. And that's the most that can happen. And you don't get any wiggling, really. Not too much wiggling. Over here, similar kind of thing. We have a vertical asymptote at x equal to 4, horizontal asymptote on the x-axis, and smooth and continuous, smooth and unbroken, and positive. And then here we go from positive to negative, crossing the x-axis here, and then have the vertical asymptote here, and then crossing over here, and then doing something like that. So that's what the graph looks like. Has to look something like that. So this is the graph y equals x over x minus 4, x plus 3. Vertical asymptote at 4, vertical asymptote at negative 3, because this polynomial is 0 at those 2 points, and this polynomial is not 0 at those 2 points. We cross the x-axis at x equal to 0, because the polynomial on top is 0 at x equal to 0, and the bottom is not 0. It's negative 12. And then, using these 3 points, negative 3, 0, and 4, we check whether the rational function is positive or negative on those intervals, and we get those values there. So we're climbing asymptotes here and here, and we have the horizontal asymptote here, off to the right and left this way. Okay, and that's a decent approximation of what this function looks like, what the graph of this function looks like. And we can get an actual picture. We can plug it in and get a picture of this thing, but this analysis that we did, tells us, gives us an better understanding of what's going on. So let's see, graph y equals x. Oops. Graph. Graph y equals x divided by x minus 4, x plus 3, and here we go. That is a really... Can't they do a better... let's see. It's going out to 150 and 100 on the x-axis. Let's see. Let's do x equals minus 20 to x equals 20. Maybe that'll get us a better picture. No. No. 4x to x. Ah, here we go. Okay, yeah, there it is. See? All right, so vertical asymptotes are showing, horizontal asymptote is showing. Of course, it doesn't mark the vertical asymptote for you, but it's right there at the 4. All right, and then you also have the 1 at the 3 over here. Maybe minus 20 to 20 is a bit much. Let's say minus 10 to 10. Yeah, it's maybe a nicer look at it. Okay. Let's look at another example. All right, so another example. So sketch the graph y equals x over x minus 1 squared. Okay, well, let's put a negative x here. All right, well, so we have x-intercept at x equal to 0. Or sorry, y-intercept at x equals 0. X and y-intercept. All right, so at the origin. And we also have vertical asymptotes where the bottom is equal to 0 and the top is not. So that's at x equal to 1. All right, so the top is 0 at 0 and the bottom is not. So the bottom is 0 at 1 and the top is not. All right, so we have x and y intercepts at x equal to 0 and vertical asymptote at x equal to 1. Horizontal asymptote is where? Well, the degree of the top is 1. Degree 1 on the top. What's the degree on the bottom? Degree 2 on the bottom. So horizontal asymptote at the x-axis, which is y equal to 0. And now all that's left to check is the positive and negative behavior. Well, here's 0 and here's 1. You just look where the polynomials on the top and bottom are 0, or on the top and bottom are 0. And you just test these intervals. So at x equal to minus 1, positive over positive. So it's positive here. Between 0 and 1, x equal to negative a half, say. All right, this is, x equal to positive a half. Negative over positive. So the whole thing is negative. And over here, positive, negative. And then over here, x equal to 2. So again, negative over positive, so the whole thing is negative. Okay. So here's my y-axis, here's my x-axis, and I'm going to have a vertical asymptote at x equal to 1. And I'm going to cross the x and y-axis at the origin, right there. Try that again. All right, and I'm positive here up to 0. I'm negative after 0. And I'm negative after 1, x equal to 1. So, and then I have a horizontal asymptote here. So one feature that's going to happen is I'm going to have to, I got to come up from this asymptote over, I'm going down here to negative infinity along this vertical asymptote. And then I got to climb up here, and then I got to get back down to the x-axis. So somewhere along the line, I'm going to have a local maximum. So there's got to be a local maximum in there somewhere, right? Because it's coming up from here. Well, it's going down from left to right, but from right to left, it's coming up, crossing, and then it's got to come down and hug the horizontal asymptote there. So there's got to be some sort of local maximum somewhere. And that local maximum, we cannot find it without calculus. We need calculus to find that one. And then you've got, this the graph is negative here, and then it's got to come up to the horizontal axis, but that's the graph. minus x over x minus 1 squared. Okay? So there's really not much to graphing these things, as long as the degree in the top and the bottom are relatively small. And you can factor the polynomial, you can get nice pictures of what these graphs look like. Okay, but I mean the finer details, you need some calculus to find that out. Like where's the local maximum here, and then there's also an inflection point. You're going from concave down to concave up at some point. So there's got to be some change in curvature, and that inflection, it's called an inflection point. And that inflection point is, you need calculus to find that too. But, you'll do that next semester. Or no, in 2 semesters. Take pre-calculus, then you'll take calculus. All right, so that's all for today. Email me with any questions or concerns. I will try. I know I owe you 2 homework assignments now. I'll try to get those graded for you and back to you today. Okay? All right, everybody.